It's example time. This is always the best part of these classes, is doing the examples, because that's where you actually learn how to apply all of these equations that we talk about. So let's go ahead and read through this example problem. And after we read it, we're going to go through and we'll highlight the keywords. It's always something you should do. And remember, when you're working through problems on your own, it's always a good idea to write out the whole problem statement. I know it's a pain to do it, but it's a good idea to do it. That way it helps you keep track of all of the details. Because otherwise, if you just read it in the book, you might miss something. All right, so writing it is just another way to make sure you don't miss any details. Now, let's read it. So we've got a closed system with a mass of 10 kilograms, and it's going to undergo a process during which we've got an energy transfer by work from the system of 0.147 kilojoules per kilogram. We've also got an elevation decrease of 50, that's in meters, and we've got an increase in velocity from 15 meters per second to 30 meters per second. The specific internal energy decreases by 5 kilojoules per kilogram, and gravity is going to be 9.7 meters per second squared. What we want to do is we want to find the heat transfer for this process in kilojoules. All right, so lots to read there. Now, there are quite a few keywords in here. First of all, closed is a keyword. Might not seem like a keyword to you yet, but once we start having mass flow problems, closed will indicate to you there is no mass flow. So closed is a keyword. We've got our mass. I want to make sure we pay attention to that. We've got an energy transfer by work from the system. From right here is a keyword because this tells you what sign you should use for your work term. Right? So important word right here. And then there's the value. Notice the units. We're going to talk about those in just a second. We've got an elevation decrease of 50 meters. Decrease, again, is important. Tells you about the sign. We've got an increase in velocity, and then it gives you your values. So increase also tells you about your sign. We've got a specific internal energy that's going to decrease by 5 kilojoules per kilogram. Again, notice the units here and the word specific. I'll tell you what all that means in just a second. And what we want to do is find heat transfer. So this means we want to find Q. That's what we're looking for. All right, so let's write out what we're given. So the mass is going to be 10 kilograms, and our work, which is given to us, is 0.147 kilojoules per kilogram. Now look at these units here. We got kilojoules per kilogram. Usually work is given in just kilojoules, right? That's what we've seen so far. Now it's per kilogram. So that means what they gave you is work per mass. Okay, so now we've got W over M. And that's going to be 0.147 kilojoules per kilogram. And next we've got an elevation decrease. So I'm just going to call that delta Y. So negative 50 meters for that. Negative because it's a decrease. Change in velocity, we've got an increase here. It's going to be positive because it's an increase. And subtract 30 and 15, you get 15 units or meters per second. Next, we've got specific internal energy. Now, remember before, when I introduced internal energy, I said to make note of capital U because it would make a difference. This is where it's going to make a difference. We are given specific internal energy. The symbol for that is going to be a lowercase u, and let's write out our value. This one is 5 kilojoules per kilogram. So if we're looking at the change in specific internal energy and it's decreasing, we're going to have delta U equals negative 5 kilojoules per kilogram. Now if you think back, when we were doing that energy balance work, the units were all kilojoules. Now we've got all these kilojoules per kilogram. Right, same thing we had up here with work. Now when we're talking about internal energy, we have this term specific. Anytime you see specific, that is indicating to you that it's giving you the energy per unit mass. Okay, so here we've got our work per unit mass, and our specific internal energy is kilojoules per kilogram. So if you see specific, that's telling you you've got your units per a unit of mass. That's all specific means, and typically when we have a specific term like this, we're going to use lowercase letters. So a little u will indicate to you that the units have kilograms or a unit of mass in the denominator. Okay? So make sure you distinguish between capital U and little u in your notes, because it will matter based on your units. Okay? Gravity is going to be 9.7 meters per second squared. What we want to do is find Q. Now, look at all the things we've got. We've got work given to us, we've got a change in elevation, we've got a change in velocity, we've got this change in internal energy, and we got gravity. Now all of those things should remind you of that energy balance equation. So let's write out that equation. So we got delta capital U plus delta PE plus delta KE. That equals Q minus W. Okay. That's our energy balance equation, and whenever you're in doubt, if you're asked to find work or Q, typically you can just come to this equation. Unless you're doing one of those piston cylinder assemblies with the volume change. Then go to the integral one. Otherwise, come to this equation. All right, so we're going to use this equation, and let's see what we need to do here. Notice in our equation we've got work. We don't have work per mass, we just have work. So we need to get work without that mass in it. Okay, so that's going to be our first thing we'll do. So we know work per mass is 0.147 kilojoules per kilogram. That's not what we want. We want to get rid of this mass term. Now how should we do that? You can probably guess. We'll just multiply the 0.147 by the actual mass, which happens to be 10. Okay, so work then is going to be 0.147 kilojoules per kilogram times 10 kilograms. Now check out the units, make sure they work out. Leaves us with kilojoules, that's what we want. So that gives us 1.47 kilojoules for work. All right. Now we're going to do the same thing for the internal energy that was given. In your equation you've got capital U. That means you want units of kilojoules, not kilojoules per kilogram, which is what you were given. So we need to convert this specific internal energy to just internal energy. Let's do that one next. So delta capital U over M gives you this delta U. Right, so that's going to be set equal to -5 kilojoules per kilogram. So again, all we need to do is take -5, multiply it by the mass. That gives us delta capital U. All right, so you got 5 or -5 times 10 kilograms. This gives you -50 kilojoules. And this is your delta capital U now. All right. So now we've taken care of this. We got 2 more. Q is what we're looking for. So next let's do kinetic energy. So remember our equation for that is 1/2 m times v2 squared minus v1 squared, where those are velocities. Now if we plug in our values, we get 1/2 10 kilograms times 30 meters per second, that's squared, minus 15 meters per second squared. Now if we look at this, let's go to the next line. We're going to get 3,375, and then look at your units. You've got kilograms, meters squared per second squared. So that's what you get. All right, we need everything to be in the same units because we've got 5 terms. They're all in the same equation, so they all have to have the same units. This is not kilojoules yet, so let's convert so we have everything in kilojoules. The conversion we're going to do, we're going to convert to newtons first. So 1 newton is equivalent to 1 kilogram per meter, not per meter, 1 kilogram meter per second squared. Okay. Now that gets rid of kilograms. It's going to get rid of 1 of the meters, and it's going to get rid of second squared. Now we're left with newton meters. Okay, so we want it in kilojoules. So remember the conversion from newton meter to kilojoules is 1 kilojoule per 10 to the 3rd newton meters. So this will cancel out those remaining units and leave you with kilojoules. So now you get 3.375 kilojoules. Okay. Last thing we've got, delta PE. So that's mg times our change in elevation. All right, so y2 minus y1. Now m was 10 kilograms, gravity is 9.7 meter per second squared, and then our change in elevation, we had negative 50 meters. All right. Now again, look at the units. We've got kilogram, meter squared per second squared. So you're going to need to do the same conversions we did up here. So I'm just going to write those out so you got it in your notes. So we have 1 newton per kilogram meter per second squared. Then let's convert that over to kilojoules. Like that. Okay. Now again, you can go through and make sure your units work out. So everything should cancel out except for kilojoules. So your delta PE here is going to be negative 4.85 kilojoules. Okay. Now we've got everything we need because we did KE and PE. So everything in that energy balance equation we have except for Q, and Q is what we're looking for. Now we just take our values that we've got, plug them into that equation, and solve for Q. All right, so let's call this equation 1. All right, so from that equation 1, we're going to have negative 50 kilojoules minus 4.85 kilojoules plus 3.375 kilojoules. That's going to equal Q minus 1.47 kilojoules. All right, and this is separate here. Now all we have to do is solve for Q. Easiest part of the problem here. So Q is going to be negative 50.005 kilojoules. And this is your answer. It's negative, so what does that tell us? If you go back to your sign convention, that means you've got energy going out of your system. Okay? So inside your system, it's hotter than the surroundings outside, so energy is leaving your system. Okay, it's going outside the system to the surroundings. All right, so that's how you do that one. Simple energy balance equation. Important thing to remember on these is always check your units and pay attention to terms that say specific. Okay, so just some pointers there, and always make sure you look at that sign because that gives you a big indicator of what's going on in your system. All right, guys, I'll see you on the next video.